Its 36-year mission was to explore strange new worlds, seek out anomalous cosmic rays and new plasmas, and boldly go where no probe has gone before. Voyager 1 has been making its way through outer space for over 4 decades now, and in that time it has gone above and beyond its initial mission. The spacecraft was only expected to survive for 5 years, but it has proven all estimates wrong. Now it has gone a step further. Voyager 1 has just detected unknown objects passing by in space, and this discovery has changed everything. The plasma comes from the explosion of giant stars millions of years ago, and that plasma carries with it the magnetic field of the galaxy. Join us as we uncover what these unknown objects are and how they might change the way we've looked at data forever. For the past few years, we've mainly just looked at data from inside the solar system, but thanks to Voyager 1, we now have access to data from outside as well. In August 2012, Voyager 1 officially reached the end of the solar system and crossed the heliopause. However, this wasn't an easy task. As Voyager 1 moved farther away from the Sun, the amount of sunlight available to power its instruments and systems diminished significantly. The spacecraft's power is primarily generated by 3 radioisotope thermoelectric generators, RTGs, that convert the heat produced by the natural decay of plutonium-238 into electricity. Over time, the decreasing heat output of the RTGs has resulted in a decline in available power. This reduction in power affects the operation of various systems on board, including scientific instruments, data transmission, and communication capabilities. To conserve energy, certain non-essential systems and instruments have been deactivated or placed in a dormant state. As the power continues to decline, critical systems may need to be further optimized or shut down to extend Voyager 1's operational lifespan. If it does continue to operate, it might not be as useful to us. The vast distance between Voyager 1 and Earth also presents a significant challenge in maintaining effective communication. As the spacecraft ventured into interstellar space, the signal strength weakened considerably, and it now takes over 21 hours for signals to travel from Voyager 1 to Earth. The weak signal, combined with interference from background noise, poses a substantial obstacle to successful data transmission and reception. In addition to power issues, there are temperature challenges. Transitioning from the heliosphere to interstellar space exposes Voyager 1 to different temperature conditions. Within the heliosphere, the spacecraft was closer to the Sun and experienced higher temperatures. As it ventured into interstellar space, it encountered extremely low temperatures, which can impact the spacecraft's materials, electronic components, and systems. Thermal stress and thermal expansion and contraction cycles might affect the structural integrity of certain parts. Extreme cold can cause materials to become brittle, potentially leading to fractures or degradation of seals and connectors. These temperature variations also influence the performance of the RTGs, which are designed to operate within specific thermal ranges. Cooling of the RTGs reduces power output, exacerbating the power challenges. Interstellar space isn't entirely empty. It contains a sparse distribution of dust particles. Although these particles are minuscule, they can pose a risk to Voyager 1. When the spacecraft encounters interstellar dust, the particles can collide with its exterior surfaces, causing wear and tear on protective coatings, antenna surfaces, or other sensitive areas. The accumulation of dust on the instrument's optics or sensors can interfere with their functionality, degrading data quality. Voyager 1 carries a dust detector instrument specifically designed to measure the density of interstellar dust. Additionally, the Deep Space Network, NASA's global system of antennas for communicating with deep space machines, must allocate limited resources to receive Voyager 1 signals, making communication opportunities less frequent than before. Amidst the stream of data, a fascinating discovery emerged. Voyager 1 detected an intriguing anomaly, a bunch of signals, most of them hard to decipher. However, one indicated the presence of 300 known objects passing by in the cosmic expanse. These mysterious entities, emerging from the depths of interstellar space, had scientists all over the world perplexed. The discovery of these 300 unidentified objects challenges our understanding of the cosmos. Are they remnants of ancient celestial bodies, drifting relics from distant star systems, or do they signify the existence of previously unknown phenomena, uncharted realms waiting to be unraveled? Normally, when Voyager sends information, it's pretty easy to decipher, but this data was scrambled. So while there were lots of questions, there weren't really any answers. However, things took a weirder turn. Despite the peculiar nature of the transmitted data, Voyager 1 itself remains seemingly unscathed, functioning in remarkable condition. The great thing was the fact that its communication link with Earth remained intact, the signal retaining its strength and allowing valuable information to be sent to NASA without much issue. The investigation revealed that, curiously, none of the spacecraft's fault protection systems were triggered, indicating that it hadn't even gone into a protective safe mode, which would be the normal course of action if it detected any threats. So it was clear that Voyager wasn't really under attack. But then, what could be causing the telemetry data to appear scrambled or inaccurate? Was it a result of interference from external cosmic phenomena, such as radiation or high-energy particles? Or was it possible that an entirely unknown phenomenon was at play? If the last one was the case, it would challenge our understanding of space and communication in the interstellar realm. The only way to know for sure, though, was to meticulously analyze a vast array of potential factors. The research team at NASA carefully examined the spacecraft systems, considering the impact of cosmic radiation on electronic components and the possibility of temperature fluctuations affecting the stability of its sensitive instruments. It was possible that something was going on right before Voyager hit the heliosphere, and the natural challenges in the way led to the scrambling of data. But the only problem was that it wasn't really in the area where the natural challenges were concentrated enough to even pose a threat. The team also scrutinized the intricacies of Voyager 1's communication systems, investigating potential signal distortions caused by cosmic noise interference or even subtle shifts in its trajectory. The search for answers led the team to meticulously analyze potential factors. They carefully examined the spacecraft systems, considering the impact of cosmic radiation on electronic components and the possibility of temperature fluctuations affecting the stability of its sensitive instruments. While all of this sounds like a checklist, there's a lot that actually goes into it, and the research went on for weeks. The team employed advanced data processing techniques, developed innovative algorithms, and simulated various scenarios to isolate the root cause of the unusual telemetry anomalies. At that point, this was the only way they could figure out what might be causing the issues. All that work didn't go to waste. After months of receiving scrambled data from the spacecraft, scientists and engineers finally restored the clarity and reliability of the information streaming in from the far reaches of interstellar space. The root cause of the problem was traced back to Voyager 1's Attitude Articulation and Control System, ACS. Specifically, an unexpected source: a dormant onboard computer. Now you might be wondering how something that's not even supposed to be functional could cause issues. NASA officials revealed that the ACS had somehow started utilizing a computer that had been non-functional for years, leading to the corruption of the transmitted data. The rest of the spacecraft, however, remained operational and continued its data collection activities unimpeded. Upon discovering the source of the problem, engineers quickly devised a solution. They sent a command to Voyager 1 instructing the ACS system to switch to the correct computer for transmitting the telemetry data. While this fix was relatively low risk, it required a lot of patience due to the significant time delay caused by the sheer distance between Earth and Voyager 1, with radio signals taking nearly 22 hours to travel back and forth. The troubleshooting process needed extreme coordination, but there was just one problem. Considering that Voyager 1 was built decades ago and had been functioning just fine until this point, to even get to troubleshooting, they needed to go through several manuals from the 1970s. And they did just that. After careful examination, they discovered a simple and low-risk solution to the problem. By resetting the system responsible for data transmission, they were able to fix the issue without messing with any other parts of the spacecraft. The engineers' expertise and dedication played a crucial role in successfully restoring the clarity of Voyager 1's communication stream. Their efforts showed the importance of leveraging past knowledge and combining it with present technology to overcome challenges in space exploration. Engineers suspect that Voyager 1's deviation into utilizing the non-operational computer was triggered by a faulty command received from another onboard system. This hypothesis suggests the presence of an underlying issue within the spacecraft's intricate computer network. Despite the concern, mission managers remain cautiously optimistic, emphasizing that the incident doesn't pose a significant threat to Voyager 1's long-term well-being. In fact, Voyager rushed through the heliopause error and went on with its mission right after the correct computers were back online. With that, it made history by successfully reaching the heliopause, the boundary that marks the outer reaches of our solar system, located where the sun's solar wind reaches the interstellar medium. It marks the edge of the heliosphere, the region influenced by the sun's magnetic field and energetic particles. It's approximately 123 astronomical units from the sun, equivalent to a staggering 11 billion miles. The heliopause is positioned at a vast distance from our star, to say the least. The heliopause is unique. Its shape is subject to fluctuations influenced by the interstellar gas wind caused by the sun's motion through space. As the sun travels, it creates a magnetic bubble or foam within this boundary, shaping the heliosphere's outermost region. This magnetic foam contributes to the intricate structure and behavior of the heliopause. When Voyager 1 and future spacecraft cross the heliopause, several things happen. First of all, there is a notable drop in the temperature of the solar wind-charged particles, which occurs as the spacecraft moves beyond the influence of the sun's direct emissions. This alone is enough to render most spacecraft useless, but despite not even being built to get that far, Voyager just went full speed ahead anyway. Additionally, there was a change in the direction of the magnetic field, reflecting the altered influence of interstellar magnetic forces. Plus, there was a significant increase in the presence of galactic cosmic rays, high-energy particles from distant cosmic sources that become more prominent beyond the heliopause but start to appear right before it. Voyager 1, being the first of the twin spacecraft to reach this momentous milestone, provided humanity with its initial glimpse into the uncharted territories beyond the heliopause, shedding light on the mysterious transition from the sun's light to deep space. In November 2018, Voyager 2 followed in its predecessor's footsteps, crossing the heliopause and venturing into interstellar space. This historic achievement marked a new chapter in our understanding of the boundary between the sun's realm and the interstellar medium. Voyager 2's encounter with the heliopause provided scientists with a unique opportunity to compare and contrast the observations made by both spacecraft, deepening our understanding of the celestial frontier. As Voyager 2 ventured beyond the heliopause, it made intriguing discoveries that added to our knowledge of this unexplored region. One notable observation was the sharp increase in the intensity of low-energy ions, which is a direct result of leaving the influence of the sun's direct emissions. Voyager 2 actually detected a simultaneous increase in the intensity of cosmic rays, high-energy particles originating from distant cosmic sources. Unlike Voyager 1, which experienced precursor events preceding its exit from the heliosphere, Voyager 2 encountered a different scenario. Instead of precursor events, Voyager 2 unveiled the presence of a distinct boundary layer located just beyond the heliopause. In this boundary layer, low-energy particles streamed outward along the Milky Way, painting a fascinating picture of the intricate dynamics occurring at the interface of our solar system and the interstellar medium as a whole. This unexpected finding highlighted the complexity of the interstellar boundary and how it might not be the easiest thing to predict. If two spacecraft that were seemingly the same had totally different experiences, it's hard to say how things would be for other spacecraft going through the same area. Is NASA really going to be willing to spend billions of dollars and put it all on the line, knowing the potential of it all going to waste? Well, as unbelievable as it might be, despite how powerful the heliosphere is, NASA wants to know everything there is to know about it and beyond. The interstellar probe is going to be the one to gather all the info. The interstellar probe is an ambitious NASA space probe concept that aims to take things one step further than the Voyager spacecraft did. First proposed in 2018 by NASA's Applied Physics Laboratory, this groundbreaking mission envisions launching the probe between 2036 and 2041, embarking on a journey that will span several decades and cover hundreds of astronomical units away from Earth. At the heart of the interstellar probe's mission is the need to gather comprehensive measurements and insights into the conditions prevailing throughout the heliosphere and the heliosheath. Yes, there's a difference between the two. The heliosphere refers to the region influenced by the sun's solar wind, while the heliosheath represents the outer layer of the sun's bubble of charged particles. With the utilization of advanced contemporary technology, the interstellar probe represents a significant leap forward in interstellar exploration.